Hello and welcome. The air quality indoors is a critical factor that directly affects the formation of the microclimate, safety, and comfortable stay for people. The main parameters determining indoor air quality are the airflow velocity, temperature, and humidity. The requirements for these parameters depend on the purpose of the room and are specified by the relevant sanitary and hygiene standards, as outlined in the following documents in Ukraine. It should be noted that not all existing measuring instruments can fully satisfy users' needs for quality and comprehensive measurements. This is especially true for measuring airflow velocities below 1 meter per second, which, according to current regulatory documentation, must be maintained indoors. The high cost of acoustic devices for measuring airflow parameters further limits their use. The aim of the work is to develop an ultrasonic device with functions for measuring airflow velocity, direction, duration, temperature, and humidity. The device is based on the property of ultrasound to change its velocity under the influence of airflow. Through experimentation, I determined that for ultra-low velocities, a two-channel bidirectional measurement scheme is most suitable. In this design, there are two ultrasonic channels positioned perpendicularly to each other in the horizontal plane. Each channel consists of two pairs of ultrasonic sensors. In each pair, one sensor acts as the transmitter of the ultrasonic signal, while the other serves as the receiver. For calculations, the following formulas must be used. The device is structurally composed of a frame that houses 4 measurement units and an electronics block, which includes 4 ultrasonic rangefinder boards, a Wi-Fi board, and a temperature and humidity sensor. Each measurement unit consists of 2 ultrasonic sensors from the RCSR04 rangefinder set. The device operation is controlled via a non-MCU Wi-Fi module based on the ESP8266 microcontroller. Temperature and humidity measurements are performed using the DHT11 sensor. The device requires an uninterrupted power source with a 5 volts output, for example, a power bank. A USB Type-C port is used to connect the power source to the device. Electrical signals from the HTSR04 rangefinder boards and the DHT11 sensor are sent to the digital inputs of the non-MCU module, where they are processed according to the installed software developed in the Arduino IDE. The functionality test was conducted using a demonstration prototype of the device. The prototype was assembled on a frame made of plastic pipes on which 4 measurement units were mounted, forming 2 partially perpendicular acoustic channels, each 36 cm long. The plastic housings of the measuring units are an original design and were manufactured using 3D printing. An airflow is generated using an air mass movement simulator, which allows manual adjustment of the airflow speed via a dimmer. The measurement results are transmitted from the device to a computer directly using the free open-source application PLXDQ, enabling further processing with standard Excel tools. Now let's conduct an experiment to see how it all works. I place the device prototype on a horizontal surface, aligning the marker to the north, and position the airflow simulator to the southwest relative to the north. Then I turn on the simulator and data regarding the number of measurements, the interval between them set programmatically for debugging purposes, speed, direction, duration, temperature, and humidity start streaming in real time. We can see them appearing in the Excel table. This allows us to analyze the results immediately and respond to changes. Now I change the simulator's direction to the northwest relative to the north. You can see how the data quickly updates in Excel, with all indicators being logged automatically. The research task was fully completed and the goal was achieved. The results of multiple experiments confirmed the device's functionality. As a result of the study, a device was developed that performs measurements of airspeed, direction, duration, temperature, and humidity indoors. The created device has several advantages compared to existing analogs. Extended functionality, including the ability to measure airflows with speeds less than 1 meter per second. ease of manufacturing and application, data processing with standard Excel tools, open source software, hardware compatibility with IoT technologies. The research has practical significance and its results can be applied to hygienic studies, air quality measurements, wind load assessments, and other areas. This all for today. Stay safe and take care. Thank you for watching.